Thanks a lot, Susanna. Thanks for having us. Yeah, very exciting today to talk about transformers, and we want to give you like an introduction how to use transformers and what you can do with transformers. Before we get into it, I mean, Susanna already gave a really nice introduction about us. Just one more thing that I would like to mention is that on the one hand is we are also working on a course. Part 1 is already out. In November, we are releasing part 2 of the Hugging Face course, where you can learn everything about transformers. And in parallel, Lewis and I are also working on a book with O'Reilly, where we want to give you everything that you need to build language applications with transform models. And our other occupation, as Susanna mentioned, we're both like machine learning engineers in the open source team. So we're contributing to the open source libraries. Here is a list of the workshop materials. We'll also post them in the chat, and I'll bring them up again when you need them. First thing is we're going to use notebooks for the demos, and you can find these notebooks on the GitHub page. Under Hugging Face workshops, there is a folder for the Tokyo workshop. Later on, you'll also need a Hugging Face login and a Hugging Face account, and you can easily create one when you go to Hugging Face /join, and can set up an account. That should only take 1 minute. And in addition to that, today we're going to showcase like a cool demo tool that we've been working on called Spaces. And to access Spaces, it's still in beta. So to access it, you need that special link that I show here. I'll show it again a little bit later on when we get to Spaces. And the last thing that Susanna already mentioned is we also have a Discord channel. So if you have questions or you want to show something to the other participants, just post it on Discord. There is a channel for the workshop as well. So what are we planning to do today? This is our plan of attack. It's like having 3 parts. The first part is giving you a little introduction into what transformers are for those of you who are not so familiar with the transformer architecture. So why is it exciting and why are people using it? In the second part, I'm going to show you a little bit map of the Hugging Face ecosystem. So how Hugging Face connects to transformers, and how you can use the Hugging Face ecosystem to build applications with transformers. And then probably the most exciting part, the last part, is applications. That's going to be a really hands-on thing where we show you how you actually load transformers, how you can use them to process text. And I'm going to show it like on a very high level. And Lewis is then going to show it like in more depth by training a model and creating a demo. And so that's like a rough timeline for today. The first 45 minutes is going to be more like a slideshow where I walk you through transformers and the Hugging Face ecosystem. Then I give like a practical overview over the NLP applications that you can do with transformers by actually showcasing them. Then we're going to take a 15-minute break just to recover a little bit. And in the last 90 minutes, Lewis is going to show you how you start by training a new model for your special use case and how to deploy it in like 90 minutes.
Just a point, Leandro, if you have questions, then just feel free to just chuck them in the chat, or even better, put them in Discord, and then we will answer them live as we go. So don't be shy.
Exactly. Yeah, it's much more fun if it's a little bit interactive, even though it's a challenging thing with 150 people now. Okay, so maybe you've already encountered some transformers in the wild at the moment, like they're popping up everywhere. One really exciting application that has recently been released is Copilot. That's a tool in a collaboration between GitHub and OpenAI. And it's essentially a model, a fancy autocomplete function. So you can enter a little bit of text or code, and that transform model predicts like the next few lines of code for you. And that can obviously make your life very easy if that works well. And people are testing it right now. And I think you can request beta access if you want to use it. Another really cool thing that probably happened today without you knowing is that you already used the transformer today. So if you use Google today, there's a really high chance that your search query was enriched with a transform model. Google is famously using a transform model called BERT now to make search queries better. And lastly, like a thing that personally really excites me, both Lewis and I are former physicists, so close to science, is work by DeepMind, where they use transform models to predict the folding of proteins. Traditionally, that has been like a really hard problem, how to predict the structure of a protein just based on its constituents. So if you know like what parts it's made of, it's not so easy to then calculate how it eventually forms and what shape it takes. And DeepMind has recently made a lot of progress in that direction, where they trained really high performance models in that area that make really accurate predictions. So where do transformers actually come from? Or what is a transformer? They were introduced like a couple of years ago in a landmark paper that was called "Attention is All You Need." And that paper created like a big wave in NLP and has changed the field since. So since the introduction of that paper, a lot of follow-up work has come from it, where people have used that new architecture that they introduced in that paper called "Attention is All You Need." But if you go into that paper, you find like a diagram like on the left that describes the architecture. And this was more or less my face when I first saw it. I mean, it's a really complicated diagram, and you don't really know what to make of it when you first look at it. And what I want to start doing now is like just give you a little bit of motivation where that architecture comes from and what it actually does and why it was so different to the things that were before it. To make the transformers actually work in practice and create that kind of NLP revolution, it required three main ingredients. One was the attention mechanism. That might not be so surprising since the paper was called "Attention is All You Need." So attention is something that's really important for the transformer architecture. But there were two more things really important to make transformers work well for practical application. And one was self-supervised learning. We'll refer to that also as like just pre-training. And this is where really the hard work goes in, and you need a lot of compute and effort to make that work well. And traditionally that's done like by really big companies. And then you can use an approach that's called transfer learning, excuse me, where you just take one of these pre-trained models and you can just fine tune it for your use case without a lot of compute and without a lot of data. And I'm going to show you a little bit more in detail what that actually means. But let's first see like where that attention mechanism comes from and what it actually does. So traditionally, when you try to build, like, for example, a translation model a couple of years ago, this was kind of the standard architecture. The building blocks of an attention of a translation system, or most NLP architectures for that matter, is like a thing called an RNN, a recurrent neural network, which is a network that has kind of a memory, and it passes its output to itself. And you can see here how that works. On the left-hand side, you have an RNN cell, and it gets some input, for example, transformers. It processes that information, and then it feeds some information to itself in the future when it then has to process the word R. And then that process continues. it creates, again, an output that it feeds to itself in the next step, and it needs to process the word crate, and so on. This is called like the encoder step, where you take an input and you encode it in a state. That's what comes out of that encoder block. That state is then used in the decoder block, where again, a different RNN cell is used to then decode that information from the state into the new language. So here is an example of English to German. So the RNN cell then needs to predict what is the corresponding sentence in German. And it does the same thing again. So it takes the state as an input and then predicts transformers, and then feeds some information to itself in the next step when it needs to predict the word sind, and so on. So that process continues until you finished your translation. That state in the middle, that's essentially just a vector. So that's just a list of numbers that's created in the encoder block. And one thing that's not so good about this architecture is that that state can create like an information bottleneck. And what's meant by that, imagine, for example, that you have things like an exact date on the left-hand side. Then that exact date, for example, it could be today. Today is the 22nd of October. That's somewhere written on the left-hand side. That needs to be exactly encoded in the state. Otherwise, the decoder can't retrieve it. So if the encoder block doesn't encode that information really good in the state, then the decoder has no chance to actually decode it. And you can imagine if you have like really long sentences or even passages, and you need to encode all the information in that passage very accurately so that the decoder block can then generate the whole translation, that is a pretty challenging task. So ideally, we would like to pass a little bit more information to the decoder than just one single state. You could imagine like sending a state for each input to the decoder, but that's also challenging because then the decoder has to deal with many states, and that creates like a huge input for the decoder block. So not so long ago, people came up with a solution to the problem, and that was called like attention, and was like a mechanism to deal with these issues. So the idea is that, in fact, the encoder creates a state for each input that it gets. So when it processes transformers, it feeds some information forward to itself, but also it creates like state number one. And it does that for all the inputs that there are to translate. And then on the other hand, the decoder now has the attention mechanism, and what it does, it helps it essentially prioritize these states. So when the model in that case needs to translate the word after transformers, it needs to predict the word sind, then it can use the attention mechanism to kind of look around the states and just pull the information that's necessary to predict that next word. And in very simple terms, what the attention mechanism essentially does, it creates like a weighted sum or a weighted average of the states. So for each state, it creates a weight and says, that's probably important or that's not important. And then it sums this state up and uses that information to make a prediction. Now, when you look at what that actually does, it helps the decoder align the tokens from the encoder or the states from the encoder with the tokens it needs to predict. And here's an example of like an English to French translation. And each pixel corresponds to that weight, to that attention the model pays at each step. And if the pixel is on the diagonal, that means that when processing a word, it looks at the word at the same position. So when looking, can you see my mouse, by the way? Or should I use?
Looks good to me.
Okay, cool. So when it translates the word de, when it needs to translate the word de, it looks at that word to then predict the word L, which is the same thing in French, and so on. So you see, it's pretty well aligned. But then there's the European Economic Area, and in French, actually the word order is turned around, and you can see that this is reflected in the attention. So the model knows when translating the word after la, which is zone, it shouldn't look at the same position, which would be European, but it should look at area, which is the word translated to English. So it knows where to look when it needs to translate the scrambled, in a sense, word order. And you can see the same thing further down, where there's the part where it says was signed. And in French, that's actually 3 words. It's a été signé. And you can see a été is, when it needs to translate this, it looks at the whole part in English. And so you can see how the attention mechanism helps the decoder look at the important parts that it needs to make a good translation at each step.
So Leandro, we have a question that's quite interesting. So the question is from Aman, and they're asking, is each state basically one word before the translation, or is it something else?
Let me see.
So I think the question is like, so, do you have for every word a corresponding state, or is it slightly different?
Okay, yeah, that's a good question. That depends a little bit on how you build the encoder block, and that's also something that you're going to see in Lewis' part, where it depends on how you process the text and how you split the text in smaller pieces. Here, a simple approach that was earlier often done is you just split in words, and then each word gets a state. Today, we're going to see a slightly different approach, which is called like subword tokenization, where you can also split words if they're very long, and that makes the vocabulary very efficient. And Louis is going to talk about that a little bit more, so I'm not going into detail now, but like the short answer is yes, kind of words, but also it can also be like smaller parts and words.
And there's just one more question on this slide here, which I think is really interesting, from Kartik, who asks, do we have a corpus of the vocab, or a different corpus for both languages when we want to train these kind of models?
I think many translation models have just one corpus. So you combine the corpus from English and French when you, in the encoder and the decoder. I think that's the question, right?
Yeah, I think it's like, do you have a sort of shared vocabulary, I guess, between the two languages?
Yeah, I think in most Transformers architecture nowadays, you have just one vocabulary, which is the merged vocabulary of both languages. Cool. I'll continue, and you just interrupt me if you have any more questions. So what does the transformer actually do? It takes that idea that I just showed of having like an attention mechanism in the decoder block and introduces it also in the encoder block. So instead of parsing one token after another, there's now an attention mechanism, and the model can use every token for each state to produce like a useful state for that. So you can imagine here the encoder needs to create a useful state for the word R, but at the same time it can also look at the surrounding tokens, so you can see what are the words next to it, and maybe that influences in what the state for that word should be. And another thing that you can see here is that actually we got rid of that RNN cell. So before, and I quickly go back, we had that RNN cell that always feeds something back to itself at each time step. In the transform architecture, there's no RNN anymore, so there's no recurrence. So at each step, there's only a feed forward neural network. That means that network doesn't feed information to the next step. And that little tweak.
Maybe We're back in action.
Sorry about that.
No worries. Okay, so actually that very small tweak of just removing that recurrence, I mean, it looks small on that diagram, but actually what it does, it makes these transformers much more easy to scale and train with more data. And that's actually a critical component of transform models, that you can train them at a very large scale, which wouldn't be easily possible if you would use these RNN cells. Yes, so coming from that diagram, pretty quickly, there were like three sub-architectures that evolved from the original transformer. That diagram we saw just now with the encoder block and the decoder block, that's usually referred to together as the transformer. There's a subfamily that was started by a model that was called BERT, which only uses an encoder. These models are usually very good at tasks that we call natural understanding tasks, or NLU tasks. And these include all sorts of classification tasks, for example, sequence classification or token classification. Also question answering is one of these tasks. And these blue models, they're really good at that. And they don't actually need a decoder because they don't generate a text at the end. They just want to make a prediction on, for example, a class. So they only use an encoder. Another subfamily that quickly evolved from the transformer architecture and that's now really popular is the GPT family of models. And that family actually only generates text, but doesn't have like an explicit like input text, like we saw before in translation, where you have a clear difference between what's the input sequence and what's the output sequence. And the GPT models, they're just good at continuing text essentially. And for that, you can only use a decoder. But also the transformer itself is still really popular. And one prominent architecture that uses the full encoder decoder stack is called T5. That can, for example, do many tasks that you can show as like sequence to sequence tasks. So you have an input sequence and an output sequence like translation. But in general, like the term
Oh, sorry, I interrupted. Carry on.
I mean, I just want to mention that in general, like the word transformer, it's very overloaded. So when people talk about transformer, they don't only mean encoder and decoder. People also refer to as BERT as a transformer or GPT as a transformer, but essentially they're like a part of transformer.
Yeah, so there's an interesting question. Yeah, exactly. From Naved, who is basically asking like, transformers also can be applied to other domains. And do you have a comment on kind of what applications beyond NLP transformers can be used for?
Yeah, I mean, we're going to see a few examples a little bit later on, but essentially transformers are branching out into all kinds of machine learning tasks. So transformers are now very prominent in vision. So people use transformer architecture, for example. Vision transformer is one example of that, to train vision models. Another very exciting field is audio. So transformer models can also be used for tasks like speech to text, where you input a voice recording, and the task of the model is to predict or to essentially write a transcript of the voice recording. And I mean, at the moment, they're used all over the place. So I think it's a whole subfield just trying to apply transformer to a new problem. So at the moment, I haven't seen a thing where people say it can't work for that architecture. I think, or for that type of problem. I think people are using them now all over the place. But we're going to look at a few concrete examples later on. Is there? Cool.
I think that's all good.
Good. So we talked a little bit now about like the three parts that you need. that were needed to make the transformers really useful for practical application. And now I'm talking about like the two others, which are pre-training and fine-tuning. And let's first have a look at pre-training. So pre-training is the step where you take a model, a new model that's randomly initialized, doesn't have any prior knowledge, and you train it on a task or on a, exactly, you train it on a task on a very large corpus, and that usually costs a lot of money, and it takes several days or nowadays even months to run the training. But that will give you like the pre-trained language model. And what that task is for many transformers, it's just predicting the next token. So you input the model with some text. For example, you can give the model the word my, and you want the model to predict the next word. And in that case, I say, the next word I want to see is name. And then you use that predicted word, and now you have my name, and you want the model to predict the next word after that. So it gets as an input my name, and it needs to predict is. After that, you say now the input to the model is my name is, and it needs to predict the next token after that. And in that case, it's Sylvain, and so on. And that task is usually referred to as language modeling. So you're predicting the next token based on the previous tokens, or tokens is similar to a word in that sense. So you're trying to predict the next word based on the previous words. This is often used, this approach is used, for example, for these GPT models. They're trained that way. And the elegance of this approach is you actually don't need any labeled data for that. If you have a text file, then the text file itself is the label when you do training, right? Because the next words are already in the text file. So you can just use the text file, feed it to the model, and train it on the text file. Usually you need a little bit more than just one file. Usually you need like a large corpus, and people are training these models on large extracts from the internet, for example, or other data sets which contain like gigabytes or terabytes of data. A related task to that, for mainly used for these bird models, is you don't predict the next token, but you predict randomly masked tokens. So you take a text and you delete a few words here and there, and then you have the model to predict what the words were that you deleted. And it's a very similar task to the previous one, but it works really well for these bird type of models. So you take that task of predicting words, you take a large corpus of text files, and then you train these models for a few days or months or weeks, depending on how large it is. And that's really expensive and requires hundreds of GPUs, thousands of GPUs to do. And then comes like the second step, and that's the step that you actually usually work on. The pre-training, that's luckily often done by large companies like Google or Facebook, that then release these pre-trained models. And you can then only do the fine-tuning, which is the second step. And in fine-tuning, you take your specific data set, maybe you want to build a sentiment classifier, and you just tune that pre-trained model a little bit on that task. And usually that works really well. So you can, most models you can train on a single GPU. You can do it on a data set that maybe has a few hundred or 1,000 examples. And that's also easily reproducible because it's not expensive to do. So everybody can do that on a GPU in a few hours on most data set. And then that then gives you like the fine-tuned data set that you can use for your use case. And this approach, like the pre-training and fine-tuning, that's what's usually called transfer learning, because you can make use of all that knowledge the model acquires by just predicting the next token or predicting missing tokens. And you can leverage that to fine-tune a model for your use case, because you couldn't train a bird model on your classification task with 100 samples from scratch. That wouldn't work. You need the pre-trained model to make it work on that little data. So although
just a question,
transformer
Leandro,
model
on that point, can you go back to the previous slide? So we have a question from Shippy who's asking, if we want to fine tune data, how large does the data set need to be to get good results?
Yeah, so you should never ask that question to a data scientist. It's like the forbidden question. I mean, the answer is always more is better. And if you have like 100,000 really good samples, then that's always better than just having 1,000. But in general, just to give you a feeling, it's usually with just a few hundred examples or a few thousand examples. I mean, obviously it depends a lot on like what the task exactly is. If your task is like predicting complicated formulas in physics, then maybe you need much more data. But if it's something simple like sentiment classification, then you might make it work with just a few hundred examples. And in fact, that's what Lewis is going to show you. He's going to train a model on just a few thousand examples and show you that that actually already works.
Yeah, I think one thing that I've personally experienced when I worked with like domain experts is the harder the task is for humans, it kind of correlates strongly with sort of how hard the task is for the transformer. So if you're just kind of doing classification, you're just trying to look, is it spam or not spam? Then it's kind of fast for us to do that. But if you have to do, for example, like a translation, that obviously requires some knowledge of the other language. And for these tasks, it typically is, much more challenging to do this with a small amount of data.
Exactly. Any other pressing question?
Oh, that's good.
Good. So although like transformers are really cool and fancy, I just want to mention like a few challenges that you face when using transformers. And one thing is the language barrier. Many of these language models or these pre-trained models are still very English or European centric. We're going to show an example today where that's not the case, where a model has been trained on more than just European languages, and how you can actually use that, for example, for Japanese. But there's just a general tendency, I think, in the field where like most or the majority of the model is still centered around European languages. Then at least the pre-training is very data hungry. So it takes a lot of money to be able to pre-train a model. And if you conquer like a completely new domain, let's say you want to do something in chemistry where you want to predict like something based on the molecules in a protein, then you might need to pre-train a model for that. And that is still very data hungry and expensive to do. So as long as you're in the fine-tuning, on the fine-tuning side, then you're fine. That's usually not that expensive. But once you need to go to the other side and you need to actually pre-train, then it gets expensive very quickly. Another thing is that these models are, like most neural networks, pretty much black boxes. So although we can look at things like attention and look at which parts of a sentence the model looks at, that's not causality. So we don't know that the model made a prediction because it looked at that word. We can just see that it focused the attention at certain words when making predictions, but that's not causality, and we can't know why exactly it made certain predictions. And the last thing is that because these models have been trained on these large corpora from the internet, so these web crawls, for example, the data from the web usually contains a lot of like, for example, racist examples, and these get kind of imprinted during the pre-training process. And you can show that if you use, for example, a bird model to predict a missing word, and the missing word is in the sentence "a man is," you can see the man is usually like either an engineer or a doctor or something like that. And if you replace man with woman, then it's usually the woman is a nurse or a secretary and things like that. And these things get imprinted in the pre-training process. So that's kind of like the introduction to what transformers are, why they're exciting and why they're so useful. And now I want to switch gears a little bit and go from like the academic side to like industry side. I was a data scientist not too long ago. And then the question that you always ask, can I have this cool new fancy tool and can I use it in my application? And that has been like a challenging task usually. I mean, these papers, for example, you can see the attention is all you need paper. Very often nowadays, they link to a repo and maybe they have some code to reproduce the results or to train these models. But one issue with that is that because the field grew so quickly, so you can see here, BERT was introduced and then subsequently there were dozens of language models that were based on BERT. Although most of them share some code, like the code is not standardized at all. It's like they're different code bases, different APIs. Sometimes they're not documented, and sometimes they are like still in Python 2, and you have to fight with all of these issues to actually take a paper, take a cool approach that has been presented there, and apply to use case. And this is kind of where Hugging Face comes in. It's like the main question we ask is, can we do better than that? Can we make these models more accessible than just having randomly distributed GitHub repos with sort of maintained code? And we believe we can, and we try to do this via open source and open science. So we try to make science in the open. That's a project that Susanna mentioned, the big science project that we're, for example, organizing. And on the other hand, through open source with the help of the community. So we can't build everything ourselves. We build it in a community. And I think that's one of the big plus points or the big advantage that we have is that we get a lot of help from the community to make these things better. And you can see here just a few of the projects on GitHub that we're working on. There's Transformers, that's probably the most known library that we built, but we also have other libraries like datasets, tokenizers, Accelerate, and the Hugging Face Hub. And to put them a little bit in kind of a map, that's like an overview over the ecosystem that we're building. And the very central part of our ecosystem is the Hugging Face Hub. That's the thing that you see here in the middle. And we use the hub to store all these pre-trained models and also all the fine-tuned models on. So if you want to use one of these models, let's say you want to use BERT, you can easily get it via the hub. And the other thing that's also on the hub is data sets and metrics. So if you want to use a special data set, we now host like over 1,000 data sets, I think, on the hub. And you can easily access them as well via code. And that's where, for example, these libraries on the left-hand side come in. The Transformers library is the Python library that lets you then use these models in code. So with the Transformers library, you can download any of these pre-trained models or also fine-tuned models and apply them to your use case or experiment with them or train them. That's all done with the Transformers library. And you can use it, it integrates well with the datasets library, where you can then also like download any of the datasets and train model A on dataset X, for example. Another exciting thing that we've been working on is, for example, AutoNLP, which is a framework where you just upload the data to the hub, essentially, or to AutoNLP, and it then automatically trains a model for you. So you actually don't need to know any code. You just upload your data set and AutoNLP figures out what the best model is and what the best settings are for that model and trains it for you. And even if you're a machine learning engineer or a data scientist, that gives you still a very strong baseline for everyday tasks. We've also have integration with SageMaker on AWS to make training very easy on SageMaker. And then another thing that Luis is going to show you is Spaces, which is essentially a demo tool. So you can easily deploy a small demo on Spaces, and then you can share it with your friends or in a blog post, and people can access it without needing to worry about how you host such a thing. And then on the inference side, we have a few things that we've worked on. One is Infinity, which is helps you have really fast inference. So if you have high throughput, so you get many requests that you need to classify, Infinity is the thing that you can use on premise. So that's something that's like a product that you can buy and then deploy on premise to have really fast inference. We're also hosting inference on the hub. So if you upload a model to the hub, you can use it through the inference API without needing to worry about scaling or hosting. And the same thing on AWS with SageMaker, where you can also host your models. The last thing that we're not going to talk about much today are two libraries that you can use to customize training and to really make the training efficient on your hardware. And these are like Accelerate and Optimum that you can use for that. But for today, I think that's still a pretty big program. We're just gonna focus, on half of the ecosystem. Yes.
There's a question, Leandro, about, I guess, this visual that you showed, which is, we talked about fine-tuning models that are pre-trained, but suppose I want to train my own transformer from scratch. Can I do that with the current tools?
Yes, you can. I mean, fine-tuning and pre-training is not different in terms of code. The main difference is that when you do fine-tuning, you start by initializing your model from a safe checkpoint, that pre-trained checkpoint. But you can always say, I don't want to do that. I just want to train a randomly initialized model. And the Transformers library, as well as if you want to do something a little bit more customized, the Accelerate library are exactly here to do that for you. So that's definitely possible.
And just one last one about the ecosystem, which I think is really interesting, from Rohan, who's asking, what would be some pointers for like newcomers who want to contribute to the Hugging Face ecosystem? Where would you kind of suggest they start?
Sure. So I would go to the Hugging Face GitHub page. So you go to github.com/huggingface, and there you see the main libraries for that we're working on. For example, Transformers or datasets, I guess, are pretty good places to start if you want to contribute. And maybe Luis, you can share the link, but I think there's like in the documentation somewhere a link how to contribute or what are good places to start if you want to contribute. So there are even guides that help you get started, as far as I know.
Exactly. And I would just say that like a good way often to get started is to look at the issues in the library. This is where people will often post kind of like feature requests or maybe even bug reports or even documentation improvements. And if you just start with these, this is often a great way to kind of understand both how the library works really deeply, but also a way to kind of start interacting with the community and the maintainers who will kind of guide you through the process.
Awesome. Any other question, or should I continue?
Carry on. Good.
Good. So that was like the main part where I just talk and don't do much else. And now we switch to actually get working. So now I'm going to show you a few applications that you can do with transformer models. And then after that, that's going to be about like 25 minutes or so that I'm going to spend on that. And after that, we take like a 15-minute break. And then Luis is going to show you how you actually train a transformer model and how you can deploy it on Spaces. So you can share it with your friends, family, and coworkers. So to get started, you need to go to the GitHub page of the workshop. And when you get there, you see there are a few folders, and you should go to the Machine Learning Tokyo folder. That's where all the materials are for this workshop. And you can see here, these are the 3 notebooks that we're going to show you today. I'm going to show you the Transformers tour, and Lewis is going to show you text classification and the Gradio demo later on. And you can simply click on the notebook, and it should render. Sometimes GitHub takes a while to render notebooks, but then you can see the notebook. And we actually want to not only look at the notebook, but we want to run it. So we can open it in Colab by clicking on the badge on top. The only requirement, as far as I know, to run things on Colab is that you have a Google login, if I'm not mistaken. So if it doesn't work for you, then just set up a Google login, and then it should work. And if you don't want to do that, you can also run this locally. For Lewis' part, you definitely gonna need a GPU to run that in efficient time. But we strongly suggest to do it on Colab, because then you don't need to worry about any installation. Good. So I want to show you a few applications of transformers, how you can actually apply them to data. And a great place, if you just want to take a model and apply to a problem without training it, is called like the pipeline object. That's like in the Transformers library. That's like the highest level of abstraction, or one of the highest level of abstraction, where literally you feed text in and you get predictions out, and you don't need to worry about anything in between. And under the hood, that's like kind of like what the pipeline looks like. You have some pre-processing. That's where also the step happens, where you have a long string and you split it into words or subwords. That happens in the pre-processing step. Then it's fed to the model. Depending on the task, maybe there's some post-processing where the predictions of the models are cleaned up, and then you get your predictions back. If you want to know more about the pipeline and how it works, I linked here a video from the course. If you want to get started with transformers in general, I think it's a great place to look at the first part of the course and go through the videos and the examples. But just in case, I give you here like a little taste of what the course looks like. The first thing we need to do is we need to install a few things. First of all, the Transformers library. That's where most of the magic happens. But we also need the sentence piece library, which is a library that helps us tokenize text. So that does that step from taking in a long string and then splitting it in smaller pieces. So we run that, and the first time you run it, you get a warning. And if you trust us, you can run it. And the installation, usually it takes like a minute or so to get these libraries installed. I have another helper function here that just makes sure that when I have a very long string, that it's nicely wrapped and you don't need to scroll from left to right. We're gonna just see it in a second. So the installation completed. So that's all good. We can create that little wrapper thing. And we can see here that's essentially a very long string. And if I pass it to the wrapper first, then it's nicely wrapped to the side. If I wouldn't do it, I can show you what it would look like. Just so you know, there's no magic happening in here. If you don't do it, then you have to scroll from left to right. So that's the only reason that I use this helper function. So the first thing I want to do, so we define an example text. It's a customer review. It's somebody complaining to Amazon. that he ordered an Optimus Prime action figure. And unfortunately, he got like a Megatron figure, which is a Decepticon. And as a big fan of Optimus Prime, you're obviously an enemy of the Decepticons, and then signs with Bumblebee. So if you're familiar with the Transformers franchise, you probably know who these are. And if not, it doesn't really matter. It's just an example of like a customer review. So the first thing that we want to do is we want to do some sentiment analysis on that. So we want to know, is that text from a customer, does that have a positive or a negative sentiment? And to do that with a transformer, I have here like a little example of how the architecture roughly looks like. You have an input text. That text gets split into tokens. Tokens are, in a sense, words, but can also be smaller than words. For example, Krista is split in two tokens. And then these tokens are fed through the transformer encoder. That's the diagram, if you recall, that I showed you earlier. And then for each of the input tokens, you get a state, essentially. And then if you just want to do classification, we can take one of these states. Usually the transform models have like a special state just for classification. And you apply like a small neural network on top of that state that does the prediction for you. So that's a linear classifier, a feed-forward neural network that predicts whether it's positive or negative.
Just a question, Leandro.
How does that come?
At this image. So Navid is asking, why is the CLS token used here? And maybe it's also nice to explain what the CLS token is.
Yeah, so the CLS token is a special token that you add, especially for classification. So if you, later on, we're gonna classify each input token, for example, Krista, Lance, Love, San Diego, and we're gonna classify each of these tokens. But if you just want to do general classification, that's essentially just a helper token. And that creates like a special state that's usually good for classification. In the pre-training, besides just doing the mask thing, that classification token is also used to predict whether two sentences are compatible. So that's like an auxiliary thing. But you can think of it just as a helper token in a sense.
There's just a follow-up question, which I think is interesting from Manas, who asks, what is the maximum amount of length of the sentence that you can pass to an encoder?
Yeah, so that's usually measured in the number of tokens that you can pass. And the number of tokens, as I said, it's not exactly words, but it's like roughly words. And for most transform model, that maximum number of tokens is limited. For BERT models, I think it's usually around 512. For other models, for GPT models can, for example, be 1024. And more recently, there has also been some architectures that are more efficient in context that can pass longer context. And I think Big BERT can go up to 4,000 tokens. And to just give you a rough idea, like 512 tokens, that's still a pretty long paragraph that you can pass.
Great, thanks.
No worries. So how does that complex diagram look like in code? It's actually just these two lines. So we import the transformer pipeline, and then we initialize a new pipeline, and we need to tell the pipeline what type of task we want to do. And in our case, we want to do text classification. Sentiment analysis is a subclass of text classification. So we want to classify whether something is positive or negative. And we can just run this code. And one thing that you're going to observe is sometimes it takes a while to initialize the transformers on Colab. But one thing that you will see is that at the beginning, you will see a few progress bars. And what's happening under the hood is the pipeline is going to the hub and it fetches some models and some tokenizers that these model uses. and loads them up for you. So you can see, first of all, you get a warning. It says, we didn't supply a model. We just say we want to do text classification, but we didn't say which model. So it uses a default model. And that Distilbert base on case fine-tune SST2 English. That's exactly what we want. That SST2 means the Distilbert model has been fine-tuned for sentiment classification. And we're going to have a look later on the hub what that actually looks like. And then you see it downloads a bunch of files for us. The Transformers library is smart. When you execute that code again, you won't see the progress bars anymore. So what that means is we download the models once, but then they're cached. So when we load it the next time, it realizes, oh, we already downloaded this model, and then it doesn't need to download it again. And then we can just use that pipeline by passing our text to it, and it returns the prediction for that text for us. So in that case, the model, that BERT model, thinks the example that we provided is negative, and it's pretty confident with like 90% that that's actually negative and not positive. So that's pretty cool. It only takes us like 3 lines of code, and we already can do sentiment classification. But
there's a question here from Harish, which is asking, like, in this case, right, you have a default model for the classification task, and do you sort of have any intuition or reasons why that particular model was chosen as the default?
Sorry. You mean why why the transformer library chooses the Distilbert model if we pass text classification? So behind the scenes, that's just a very simple lookup. For each task, there's just a popular model that you can use. So what the pipeline didn't do, it didn't look at our text and thought, oh, that looks like a sentiment problem, so probably I should choose a sentiment model. It's much simpler than that. It just has like, most often when people do text classification, a cool thing to show is sentiment, and therefore that model was like provided to the pipeline as the default model. In most cases, you would do it the other way around. You would probably go to the hub and select the model that you want to test, and we're going to do that in a second. And then once you have a model that you think fits your use case, you go to the pipeline, and then you specifically say, I don't want to use the default one. I want to use that special one because I think that's the best one for my use case. But just for now, I mean, the standard models are just a good start if you just want to showcase it or you want to know like how text classification goes. I hope that answers the question.
Great, thanks.
Yeah, and so we're going to actually now do something that's even a little bit more complicated from the diagram perspective. And we're going to do something that's called entity recognition. So we want to detect entities in a text. So we have a text, the same text as before. For example, Krista loves San Diego. And there are different kinds of entities in the text. On the one hand, there's like a person. Krista Lanz is a person. And we have a location, San Diego. And one thing that can be very useful is to extract these kind of information from text. Let's say you're dealing again with customer feedback. It can help if you can extract the names, maybe, of the customer or an employee that the customer is referring to, or maybe a product that the customer is mentioning. If you can extract all this information from a text, you can do useful things with it and maybe automatically then forward the email to the person responsible for that product line, for example. And so how can we do that in the Transformers library? It's pretty simple. Actually, we just need to provide a different task. So instead of text classification, we now say we want to do named entity recognition. And again, we just get like the standard model for that. And it's a BERT large cased model fine-tuned on that CoNLL task, which is like a canonical data set for named entity recognition that has a few classes. If I remember correctly, it has persons, location, and miscellaneous as classes. And maybe for your use case, that's not so useful, but just to showcase how the model looks in practice, we're going to use that one. And you can see that one is already a little bit bigger. The previous one was only a few hundred megabytes. That one is now a few gigabytes. It takes a little bit longer to download. And the other bars that you can see, this is like meta information and the tokenizer that's also downloaded to make sure that we load the model with the right configuration. And then we can again pass our text to the pipeline. And in addition, we can use an aggregation strategy. And if we go back to that diagram here, what the aggregation strategy is we have, for example, for Crystal Lanz, we have 3 tokens. And you can see we get a beginning person, and then we get a special token for a follow-up token after the beginning. So we know if there's a B person and an I person, those 2 actually belong together. One is the beginning and one is the follow-up token. And with the aggregation strategy, we can just merge these and say, Crystal Lanz is a person, instead of saying CHR is a person and Ista is a person and Lanz is a person. So that's just a helper thing. We can just say aggregate these for us. And you can see you get like a long list with entities. If we just pick one, we can see, there's another one that I forgot to mention. There's organization. So we can see the model said Amazon is an organization with like a certain confidence. And the start end that you see, that corresponds to the start and end character in the text. So it tells you where in the text Amazon was. And we can also clean that up a little bit, print it a little bit in this. I didn't actually run that. So we can print it up, clean that up a little bit. So you can see Amazon was identified as an organization. Optimus Prime was miscellaneous. Germany is a location. And then you can see for Megatron Decepticons, the model got a little bit confused. It thought like the first token of Megatron is miscellaneous and the second half is probably a person. That's why they also weren't merged. And a similar thing happened to Decepticons, where it thought the first part is an organization and the second part is miscellaneous. That's not so unexpected because we used a pre-trained model that probably wasn't trained on a transformer character data set. So it doesn't know what a Megatron is. So for that reason, it's then important to fine tune this model for your actual use case if you have like special words, for example, in your data set. And that's the thing Luis is going to show you how to do, like a classifier, also on Amazon reviews. Now we can go a step further. We can do classification and we can extract entities, but we can do something that's, in my opinion, even a little bit cooler than that. And that's question answering. And question answering is the task where you have a text. For example, it's our customer review, and you can ask a question about the text. And the model needs then to predict what the answer is of your question based on the text you provide. The thing that the version of question answering that we show here is called extractive question answering. So the model just predicts where in the input text the answer is. It doesn't generate an answer from nothing. So it can only answer the question if it's present in the text you provide. This is called like extractive question answering because you just extract an answer from the text that you provide. And there are other versions of question answering where the model can, for example, maybe you don't give it any context at all, and you just give it a question and it has to answer the question. And these are like closed book question answering, for example, where the model just needs to remember things from pre-training. But here we just focus on extractive question answering. So for each token, the model is going to predict if the token is likely the start or the end of the answer to the question that we ask. And here you can also see those special tokens again. We're not using the classification one. It's usually still there, but you don't need to use it. But the one that we actually use now is the separator token. And that we put that between the question and the context. So here is a question about maybe why didn't I get the right product? And then here in red, that would be the text that we have that describes the situation. And we play the same game. We load a question answering pipeline. That's a model trained on Squad. Squad is like a very popular question answering data set from Stanford. And once it's loaded, we can actually ask a question. And for example, the question can be, what does the customer want? And the context is the text that we provide is the same text we had before. And the answer of the model is the customer wants an exchange of Megatron. And if we go quickly back to the example, here, what does the customer want? It's an exchange of Megatron. And you can see that in that example here. So the model just extracted that passage from the input text.
I've got a question here, Leandro, about the images that we have, like the diagrams. So we're often talking about, like, there's a transformer encoder, and then there are these encoder representations. And a question from John is, what exactly are these representations in these diagrams?
You're referring to by representation, you mean the hidden states?
Exactly.
Yeah. So the hidden states are the same states that we saw in the diagram I showed at the very early in the presentation, where we had that encoder and decoder architecture, and in the middle there were the states. These hidden states that you can see here are exactly the same. And what happens during pre-training, we have the mask language modeling, for example. So some of the input tokens of a text are masked, and then the hidden states are used to predict what the original token was at that position. And that's how, with that training, like the model learns like a useful representation of each token in that hidden state. And we just reuse that hidden state then for our new task. I hope that answers it. Cool. So we're gonna change topic a little bit. Until now, we did like these natural understanding tasks, which are you have an input and then the model makes a single prediction. And now we're changing gears a little bit towards natural language generation. So the model needs to generate something or generate text. And one very famous example is summarization. So we want to give the model the long text and we wanted to create a summarization from it. And we can do that. I mean, from a code perspective, it's not different. We just load a summarization pipeline that loads a BART model that has been pre-trained on CNN dataset, which is a dataset with a lot of news articles and summaries for these news articles. And we're going to use that model to see, although that has been predicted on news, if it can also predict the summary or generate the summary for our customer complaint. And one thing that you're going to notice is that generation models that need to generate, or don't need to predict, for example, a class. And the reason is, only using the model once, we actually use it many times to always predict the next token. So in that example, we have like transformers are the, and then the model predicts most. And then that's the same task I showed you for pre-training, where you always predict the next token. And every time you do that, you use your model once, whereas in the classification example, you only need to use the model one time. So our summarization pipeline has loaded, and let's see if we can generate a summary for that text. And as you can see, the summary doesn't look too bad. Bumblebee ordered an Optimus Prime action figure from an online store in Germany. One thing that's maybe a bit weird is it switches between the third person and the first person. So the second half of the summary is in the first person. So it changed point of view, but from the content, it doesn't look that bad. And if we trained it actually on a customer feedback data set, it would probably work better than on a model that was trained on a news data set. Another task that's also related to generation is called translation. So when you want to translate the text from one language to another, and I try to choose like an actual example for that. So I want to translate a sentence, for example, from English to Japanese. There's a group called the Helsinki NLP group that provides like dozens or hundreds and thousands of translation models. So you can use one of their models. For example, I chose an English to Japanese model, and we can use that model to then create a translation of, at the MLT workshop in Tokyo, we gave an introduction about Transformers. And we can use that translator to generate a translation for us. And unfortunately, I can't speak Japanese, but what we can do is just quickly check if that can possibly make any sense. And we can go to Google Translate and see if I translate that back, does that make any sense? And you can see, although like the sentence is a little bit different, the core concept is still the same. So I hope that the Japanese version makes some sense.
We actually have a question about like translations and summarization from Laura, who's asking, is the output deterministic? So if I run this pipeline multiple times, will I always get the same output?
That depends a little bit on how you're running it. You're right that it can be not deterministic. So usually the model has several possibilities that it can choose from. And so let's say when we go back to that diagram here, maybe Transformers are and the most is just one option out of many options. So another option could, for example, be maybe Transformers are the least, or Transformers are the best. So there are many options that the model has to select from at that point, and each option has the probability. And there are several ways how you then can select a token. You can just take the one with the highest probability. And if you always do that, then your model is deterministic. But you can also say I sample. So I randomly choose an option based on the probability. So if an option has a higher probability, then I have a higher chance of picking it, but I don't always pick like the one with the highest probability. And in that case, you can generate different outputs with the same input, essentially. And you can control that through the generation. You can pass some arguments where you can modify that, how the generation is done.
I also want to just mention a cool trick here with translation, which is like if you don't have a lot of data in your language. So for example, let's suppose I'm trying to build a model in Japanese, and maybe I only have like, I don't know, 100 examples in Japanese. A common trick that people use in industry is to use like a transformer to translate the Japanese examples into English or another language, and then translate back to Japanese. And as Leandro showed us, we saw that like there was a bit of a difference between the translation in Google Translate versus the original English. And this kind of noise, or this kind of slight change in the outputs, is a way of kind of creating synthetic data, which is a great way to like kind of boost the performance of your models a little bit.
Exactly. Cool. So there's a last thing I want to show you, and I'm already a little bit over time. So That's better. So you can use any model that you want in the pipeline. And I want to quickly show you how you can select one. So when you go to the hub, you can see at the moment there are 28,000 models on the Hugging Face hub, and you can download any of them in the code the same way I did now with the pipeline. And for the last example, I want to show you something cool that's called the zero shot classification model. And here on the left, you can see many tasks that are possible. So for example, there's summarization or there's question answering. I now selected zero shot classification. You can also sort for other things. You can sort for libraries, PyTorch, Tunstall, or Jax, or any others at the moment, like Spacey and so. They're all on the hub or data set that these models have been trained on. You can filter. And for example, I want to use that one because I know XLM Roberta is a multilingual model. So that looks pretty good. I have that zero shot classification task that I want to have. And I have a model that I think, based on the stats, maybe I like that one, so I can copy it. And when I go back, I can say I want to do zero shot classification. That's the task I just described. Or I didn't describe it yet. I will in a second, but that's the task I selected. And I can paste the model I want to use here with that argument model equals, and then I just pass the name of the model. Now what the zero shot classification pipeline does is usually you train a model on a specific task. So you train it to predict positive and negative sentiment. And then once you train it on that task, you can only solve that task. So you can't take a sentiment model and ask it to predict the third class because it doesn't know how to deal with these classes. And the zero shot classification model approaches the classification problem a little bit different. And instead of predicting discrete classes, it just predicts whether words are compatible. So if you have a class, maybe your class is politics and you have an input text, then it just tells you how likely the word politics and that text are compatible. And with that, you're much more flexible because now you can define your classes in text and you can define any classes that you want. And the model just tells you whether the classes are compatible with text. And we can load up that zero shot pipeline. I think that's a pretty big one. So you can see it's 2 megabytes. So it's going to take a minute to load. And what I'm going to do is I'm going to take the Japanese text that I just translated, and I want to know whether that text has anything to do with Japan, Switzerland, or the USA. And I know within the text, I said it's the meetup in Tokyo. So the model should know that, or should recognize that Tokyo is related to Japan and give us like a high probability that these two match together. And it's going to load, but you can already see like the results from a previous experiment, and the model was really good at predicting that text is about Japan. And one thing you can verify yourself if you take Tokyo out of the text. So if I don't do Tokyo here, then it's not going to predict Japan. So it's not just matching that's Japanese language, therefore the text must be about Japan. It actually looks at the content of the text. So it should have been loaded now, and we can see the predictions. Yeah, predicts Japan. And I'm gonna do something risky and just gonna demo it. And I'm just gonna change the text and remove Tokyo. And that's going to give us the translation where hopefully Tokyo is not anymore in the text. And if I replace this, you can see the model is now very confused because it doesn't, any of those could be compatible with the input text that I just used. And you can play it with yourself. You can also change the classes. You can be any string that you can enter as a class, and it will tell you whether that string is compatible. And another cool thing that you might have noticed, I'm now mixing like a Japanese input text with English labels. And because the model that I've been using is a multilingual model, that doesn't really matter. And Lewis is going to show you a multilingual model as well. So going into more detail. I'm going to wrap up now. I just want to tell you that there are many more pipelines. I just scratched the surface of some of them. For the person that asked about other modalities for transformers, you can see there's also audio classification or automatic speech recognition pipeline. There's also conversation or image classification or object detection. And one thing that's really cool is like in computer vision, you get nice widgets. So that's actually from the hub. If you go to the hub, one thing I didn't talk about that much is you can actually test all the models right here. You can enter some text and you can also compute the thing. So that's essentially the pipeline on the hub that you can use. And if you use vision models, you have a nice widget where you can actually see the predictions in the text. And there's also audio, so you can record your voice or you can use a sample and it will then transcribe that for you. And lastly, another thing that's really cool is there's question answering on tables. So you can ask a question about a table and the model predict where the answer to your question is in that table.
There's a question, yeah, Leandro, just around this. So you've shown a whole bunch of different models, and kind of general question would be like, where do you get started? Like, I mean, how do I, if I have a use case that's like, I don't know, question answering, how should I know kind of in advance which models I should start with? Like, do you have any advice for that?
Yeah, I mean, I would go to the hub, back to the hub, to the models, and you can start filtering the models for your use case. So for example, if you want to do question answering, you can have a look at question answering models. And you can also see they're sorted. So that model has been downloaded 2 million times for question answering. So maybe that's a good model because a lot of people used it. So you can give it a shot. You can also click on the model, and usually there's a lot of description about what data set the model has been trained on and what the performance was on that data set. So that should give you a feeling what a good model could be.
Yeah, I think one extra thing I would mention that I often do is there's a website called Papers with Code, which is run by Facebook, and they collect all of the academic literature on machine learning, and they summarize a lot of it in terms of leaderboards. So maybe Leandro, you can just quickly show the squad leaderboard, for example. And if you, yeah, just pick like squad 2. And then here you'll get like a super nice table showing you like which models are performing best. And then once you sort of see an interesting model, I think some of them you can even get like a link. Like if you click on one of them, like, I don't know, Albert or something. Sometimes there's a link which will then tell you like, you know, here's a link back to the hub. So not every model on Papers with Code has a link to the hub, but some of them do. And then that way, that's one way of getting the thing you want.
Yeah, that one doesn't seem to.
Yeah, sorry, I can't remember. Yeah. It's not everyone, but some of them, yeah.
Good. A last thing to mention is I mentioned that all the models are downloaded and cached. And if you run that notebook locally, probably you require now like 20 gigabytes of transform models. And so you want to eventually clean that up. And I put here like where you can find the cache and how you can clean it. Yeah, that's it from my side. I think it makes sense to make like a 5-minute break, 10-minute break. What do you think?
Yeah, how about we come back? I don't know what the time is in Japan right now, but like let's come back in say 5 minutes. How does that sound, Susanna?
Sounds great. Yeah.
Okay, so what Leandro has shown us in the last session is how to do basically inference, or how to generate predictions from models that are already available on the hub. But if you're working in industry or you're trying to build your own project with NLP, most of the time you're going to need to train your own model. And as Leandro explained, there's kind of two things you can do. One is you can train it from scratch, but that's very expensive and takes many days of computing power and a very large data set. So the most common technique that people use in practice is fine tuning. So you take a pre-trained model, which is freely available, and then you just adapt the weights of this model for the task at hand. So what we're going to do today is we're going to have a look at basically how this fine tuning works in practice. And so we're going to pick a data set from the Hugging Face hub, and then we're going to fine tune a model on it. And then at the end, we're going to push the model back to the hub that we've trained so that then we can use it for deployment or using for another application. And if you have any questions, just chuck them in the chat. And I'm pretty sure Leandro will be reading it. So, as before, we just need to install a couple of libraries. The main thing that we're going to see that's different today or in this section is that we're going to use now the datasets library. And this library is designed to be able to process huge amounts of text data in a very optimal way. So you can basically crunch through, a terabyte of data on your laptop and it won't blow up your CPU, which is really cool. Okay, so the other thing that we need to do to sort of set up is once you have your Hugging Face account, so if you go to hf.co/join, this will ask you to sign up. And if you already have an account, you'll then see in your profile what your username is. And so if we look at this, you then can do a login in Colab or in your notebook, and this will then guarantee that any model that we push to the hub will be assigned to your account. So you just have to run this, this cell and it will give you a widget. And then there's just a few small technical things. We need to configure Git and we need to configure something called Git LFS, but these aren't super important. They're just some libraries that we need to set up. Okay, so what I thought we could do today is I'm going to take a multilingual model, which is called XLM Roberta. And this model is quite interesting because it's pre-trained on 100 different languages in parallel. And then once you have this model, it's now got some kind of generic understanding of, say, English, but also perhaps Japanese and also perhaps German and maybe some other, more rare languages that you're interested in. And the cool thing here is that when we do fine tuning on one of the languages that we're interested in, the model still retains enough memory to do zero-shot transfer to another language it hasn't seen in the fine tuning step. And so the data set I'm going to use today is an Amazon reviews corpus, which has got 6 different languages. And we're going to load this and process this using the datasets library I mentioned. And if you've never heard of datasets, I recommend you check out this video by Sylvain, which is from the course. And I just want to mention also that next month, in November 15th, we're actually going to be launching the second part of the Hugging Face course, where we're going to go really deep into all the tasks of NLP. And so if there's, if what you see today is exciting and interesting, then I recommend you take part in this community event, which is going to be really cool. Okay, so I mentioned we're going to load a data set from the hub. And so the data set in question is called the Multilingual Amazon Reviews Corpus, or MARC for short. And many of the data sets on the hub, they are given like a dataset card, which explains some kind of key information about the dataset. And it's always really good if you're sharing data to make sure that you provide enough information and context so other people sort of know what they're getting. And in this case, we're told that it's a dataset of product reviews for multilingual text classification. And we're told that we've got reviews in 6 languages: English, Japanese, German, French, Chinese, and Spanish. So that looks quite interesting. And we're also told that for each language, there are 200,000, 5,000, 5,000 reviews for the training, development, and test sets. So this is actually a pretty huge data set for text classification. And then if you go down, it tells you some more meta information about the languages and so on. But I won't dive into that yet. So let's suppose this is the data set we want to use. So the first thing we want to figure out is what are the kind of available configurations in this data set. So the datasets library provides us with a helper function called get dataset config names. And then what you do is you provide the name of the dataset on the hub, and then it will automatically tell you, for example, what are the different language codes that this dataset has available. So if I run this, I should hopefully get them like this. And the reason why this is handy is like there are many data sets on the hub which have multiple subsets. So to give you another example, if you're familiar with NLP benchmarks, there's a famous one called Glue, which tests language models across many different tasks. And if we apply the get dataset config names to this, it will then tell us all of the different subtasks, so that this way we can then pick which one we're interested in when we're training our model. Cool. So here we can see that we've got a variety of language codes. So what I'm going to do is I'm going to select the English subset, and we're going to train a multilingual model on the English subset of this corpus. And then we're going to look at how well it generalizes to languages like Japanese or French. So the main thing that you start with in datasets is the load dataset function. And you just have to pass the name of the dataset on the hub and the subset you're interested in. So if I run this, it will download the various splits directly from the hub, and it will then process them for us in a data structure that is really optimized for memory. So you'll have a very small memory footprint, which means you can, in principle, download huge data sets. And as long as you've got enough disk space, the datasets library will still be able to load it. So you can see here that the output is kind of like a dictionary. So it's called a dataset dictionary. And it has keys, which are the splits. So we've got a train, test, and validation split. And all the values of these splits are themselves what's called a dataset object. And this dataset object is kind of like the central player in the whole datasets library, with which we're able to then do processing, filtering, slicing, any kind of stuff like this. And you can see here we've got some features, which are basically the columns of the dataset. And we were told how many rows we have. So we've got quite a lot of columns in this data set, and also quite a lot of data to play with. So to give you an idea of what's inside this data set, we can pick one of the keys in this data set dictionary, and this will then give us a data set object, which we can then index just like you would index like a data frame or a NumPy array or even a Python list. And so if you look at this example, we can see that the first element in our training set has a review, which is saying that there's something that arrived broken and 2 of the legs were not completely formed. And we also got told what the title of this review is, which is like, I'll spend twice the amount of time boxing up the whole useless thing, blah, 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 which is kind of indicative that it's a pretty negative review. And indeed, if we look at the number of stars that this person gave to this product, it's very low. So this is a pretty common thing you'll see if you're doing any sort of sentiment analysis, that people write, negative comments or even positive ones. And the kind of thing that's interesting for like a consumer, or sorry, for a customer or a client, is to sort of understand if you can detect these kind of extremes or these kind of sentiments, and then take some sort of action to help address the problem fast, instead of having to manually read every single thing. And the other thing that you can do, instead of just selecting one element, is you can do a slice, just like in Python. And if we do this, we then get, instead of getting a single element or a single review, we're now getting a list of different reviews to play with. So that's just like a very kind of high level peek at what we have in our data. But the really common thing that happens the first time you start playing with the datasets library is most of the time you're interested in applying or using it for your own use case. And if you are in industry, very rarely do you have access, or you're allowed to even download data from the hub or external websites. So the datasets library provides 2 main ways to basically process data that's on your laptop, or just process data that's not on the hub in general. So the first thing I'm going to show you is how to load a data set that's just locally on your machine. And what I'm going to do here is there's a URL, which is basically the URL where the Amazon review data set actually lives. So if we use this URL, we can manually download it using wget. And this file now should be visible. If I can have a look here, we should be able to see it in our file system that indeed there's a JSON file inside here. And if we maybe have another peek at it, we can maybe go, if we just look at, what is it, data set. You can see that it's basically a file where every line in the file is a JSON object. And so this kind of like data structure is very common in whenever you're processing like NLP data. So what the dataset library lets you do is you can specify, instead of saying the name of the dataset on the hub, you can provide a specific loading script. And in this case, we know it's JSON data, so we can specify that it's JSON loading script. And then we just provide the name of the file that we want to load. And the dataset library will then automatically read this file and process it in exactly the same way we saw before. So you can see here, we've now got the training set with the same columns and the same number of rows. And this process, right, involved us like downloading the file manually and then loading it locally. But a lot of the time you might have your data stored on some kind of remote server inside your organization. And here what you can do is you can just pass the URL directly to data files, and it will figure out first that you don't have it on your laptop. It will then basically download the data, and then it will load it for you also automatically this way. And there are many different loading scripts you can use. You can load CSV files, you can load text files, you can load data frames. There's many different formats that are available, and you can check out the datasets library documentation to get some idea of what that's about. Okay, so that was just like loading the data and having a quick look at it. But one thing that's like super common in data science projects is to, at some point, do some kind of complicated aggregation or do some sort of, something that's a little bit non-trivial on the data that you have. And the kind of workhorse for this is, I think, Pandas, the Pandas library. And a lot of the time, like when I've had to use other tools like Spark or other sort of, big data tools, it's always been frustrating that I have to kind of change my kind of tool set. So, I have to learn a completely new API just to be able to process some data. And the datasets library actually lets you use Pandas out of the box, which is really cool. So the way this works is you can apply a set format function to your data set, and you can then automatically convert the output of your data from this data set structure that we have kind of inbuilt to NumPy arrays, to PyTorch tensors, to TensorFlow tensors, to JAX arrays. And in this case, I'm going to show you how you do it for data frames. So we say we want to change the format to Pandas, and then we basically slice the whole data set, and this will return a big data frame. And then I'm just going to visualize quickly what this data frame looks like. And so you can see here, I've now converted this kind of dictionary structure that we saw earlier now into my favorite data structure of data frames. And we can see, we've got some reviews, we've got some titles, and we've also got some styles to play with. So at this stage, I haven't done anything. Yep.
Maybe two questions that are interesting. One is that, does a dataset library also support vision, or is there a library for vision? And another one is like, does it also support like other payloads, like encrypted payloads, like Avro, for example?
Okay, yeah, great question. So on the Avro side of things and with encrypted stuff, I'm not sure. My hunch is the answer is no at the moment. But if it's something that you need, then feel free to open an issue on the datasets library. And the first question about whether the datasets library supports computer vision, the answer is yes. And this is like a sort of active a bit of work right now. So you can, for example, get the MNIST data set by just passing MNIST from the hub. And this will now, at some point, download all these images from the Hugging Face hub, and then it will represent them as arrays. So in fact, if I just have a quick look here at MNIST, then MNIST train 0 should be, it's a big array, right? This is just the MNIST images are like these gray 28 by 28 images, and then it's just flattened out into one big vector. And we're also working on supporting audio, so you can also download audio data sets, for example, common voice or common language. Good questions.
And maybe another one is, how do you split the train data set into validation and test using the datasets library?
Okay, that's a great question.
Maybe related to that, like where do the splits come from that you currently have?
Great question. Okay, so when I downloaded the data set at the very start, let's have a look where it is here. So when I did this load data set, it came with predefined train, validation, and test splits. And these are predefined by the creators of the data set, and we don't do anything with them. But what you can do is, like, most of the time, right, if you're doing a real project, you don't have this very nice thing, prepared for you. So the datasets library has its own train test split function. So let's suppose that I've just got some my training data is just my split here. So I'm going to take one sec. Okay, so I'm going to take the training split of my data set. For some reason, Colab is really slow today. Okay, so I've got my training split. And if I wanted to now create my own custom validation and split and train split from this, what I could do is I can go train data.train train test split, and this will then automatically split the data into some fraction, which I think is I think it's probably like 80-20 or something like this. I forget. Okay, I don't see the defaults, but basically it will split the data into these fractions here for you. So this is more or less like scikit-learn, right? Like in scikit-learn, we have train test split. It's the basic same idea, and you can do this to any of your own data sets. Okay, so going back to pandas. Okay, so here I am going to set the format back to pandas. Okay, so now that we have our data set as a data frame, we can do all the cool things that we like in pandas. And one of our most used functions I'm always playing with is the value counts, when I've just got some categorical data and I just want to quickly see what the distribution of values looks like. And in this case, we're dealing with Amazon reviews. And so every review has a category associated with which type of product it is. And so if we run value counts on this data frame, we can see that, for example, the most common reviews are about home items. Then there's like apparel, which is like clothes, and then wireless and so on. And so this is kind of cool. We can just do the usual things that we do in pandas. And we can also see that, there are some very rare ones like, personal care appliances and so on. The other thing that is always really important to check is that if you're building a predictive model and you've got some labels, it's important to understand what the kind of distribution of those labels is. So in this particular case, this data set was created by academics. So it's generally very clean and very well balanced. And you can see here, for example, that every rating has 1 to 5 stars, and all the classes have the same number of examples. And so this means that the problems that can happen when you have imbalanced data, we don't have to worry about them today. And then once you're done with playing around with data frames or NumPy arrays, whatever, just remember that you should reset the format of the data set so that you go back to the original data set structure, so that then when we do future transformations, we're not transforming on data frames, we're transforming on these kind of raw dictionary objects. Okay, so that was just showing you sort of like how easy it is to switch between the dataset structure and pandas. But what I'd like to show you now is that there's basically two common operations that you're going to use in the datasets library. So the first one is like filtering data, and the second one is transforming the data with something called a map function. So I'm going to show you the filtering function first. And I thought what would be cool is like, instead of trying to train a model on all 200,000 reviews, which would actually just take a long time on Colab and also be like maybe, you know, not what we would actually do in the real world. I'm going to pick a particular category of products, and I'm going to show you how we can then filter the data set for just that product. So the way this works in data sets, if you're doing a filter or you're doing a map, these functions, they expect you to provide some logic, and that logic we represent it as a function itself. So here what I've done is I've created a function called filter for product. It takes an example from the data set and it checks whether that example has a product category which is the same as the one that I've picked, which is book. And so this will basically return true or false based on whether the review belongs to the category or not. And so then once you define the function, you just have to feed this function inside a filter function like this. And then when you apply that to your data set, it will automatically crunch through all these, 200, 300,000 reviews and just do this true false check. And then at the end, we get something which is much smaller and manageable. And you can see here, we've now got 376 reviews in our data set, in our books data set. And if we look at our distributions from before, we can see that books is indeed 3,756 here. So this is telling us that the filtering has worked. And the other thing we can just do, if we want to have a quick look to make sure just visually that, indeed we do have book data sets, book reviews, is just to take a random sample. And in data sets, you can do this by shuffling your data and then selecting some number of elements. And if we look at this example here, we can see something about Farm Animals Touch, which seems like a baby's book. And you can see that, indeed something about stories, quick read. So this seems like it is indeed a data set now about books. Cool. So that was filtering the data. And now we want to do some transformations to kind of clean it up a little bit. So the way that we can, or maybe the first thing that we should tackle is the labels. So we're told that we've got star ratings, which go from 1 to 5. But all of the models in the Transformers library expect that your labels start from 0 to n. And that's because it's a convention in computer science to kind of start counting from 0. And if we try to just feed the labels to the model, we're going to get errors. It's basically going to complain that, it expected something at position 0 and got nothing there. So what we need to do is we need to kind of change the data set labels so that instead of going from 1 to 5, we go from 0 to 4. So the first thing I'm going to do is I'm going to create a mapping for 0 to 4, and I'm going to add some kind of human readable words here that help us understand, is the review good or bad? So instead of saying 0, 1, 2, 3, 4, I'm going to create a mapping which says, okay, 0 is associated with a terrible review, whereas 4 is associated with a great review. So if I create this dictionary, then what we can do is we can use this dictionary to basically map all of the star ratings into this new ordering. And so there's a function here called map labels I've created. And so first what I do is I take the star associated with the review, I subtract 1 from it so that we go down a level. And then I just return a dictionary with 2 elements. So the first element is the ID with this new ordering. And the second element in the dictionary is the name of the label using this terrible, poor, okay, good, or great. And so one thing that is important to understand when you're doing transformations on data with data sets is that all of the map operations, they expect you to return a dictionary. And the dictionary, the keys of the dictionary will correspond to columns in the data set, and the values will correspond to the transformed values that you want to return. So in this case, I'm actually returning, I'm actually creating two new columns in the data set, one called labels and one called label name. And if this value here is the same as an existing column, it will basically override it when you're doing it. So now we've got our kind of transformation of the labels. I then just apply map and I give it the function, and then it will crunch through, again, all these book reviews, and it will now include these two new columns we created. And so if you look at this example, you can see that, for example, here, the stars of this review were 1. And indeed, the shifted labels are now 0. So that's good. That's telling us that we're going to have something the model will understand. And we've also now got the associated label name, which was terrible in this case. So this looks kind of good. And the last thing I'm just going to do is create a reverse mapping going from the label name back to the ID. And we're going to use this in the model so that then when we make predictions from the model, instead of just getting 0, 1, 2, 3, or 4, we're going to get the actual names like terrible, good, great, so on. Okay, any questions at this stage, Leandro?
No, I think fairly clear, it seems.
Cool. So what I just showed you so far is kind of like, let's say, the first few steps that almost every data science project will have. You're going to have to do some loading of the data. You're going to have to do some inspection of it. And then you're going to do some like basic preparation or, basic cleaning like we just did. So we filtered the data, for example. And once you're kind of confident that, the data set is in a good spot to start actually training a model, the very first thing we need to do is actually convert all of these reviews into these tokens that Leandro showed us. So if I just try to give a string to a model, it's going to crash because all of deep learning is basically based on matrix multiplications. And you can't easily do matrix multiplication on raw strings. And so what we need is some technique which will convert a string into some numerical representation, which is good for doing these kind of computations. So we need to create tokens. And there's a very large number of different ways you can tokenize text. And you can watch this video with Lysandra to understand the different options. But what I'm going to do today is I'm just going to take an existing tokenizer. Oops. I'm going to take an existing tokenizer that's associated with the model called XLM Roberta. And so if you want to load a tokenizer from the hub, you use the auto tokenizer class. And this auto tokenizer class is very clever. It will work out that whatever name you pass for the name of the model, it will automatically work out, you're trying to load this kind of model, and it will then basically instantiate the right class so that then it has all the right methods for the task you're studying. So in this case, we use auto tokenizer and the from pre-trained function. And this is now downloading from the hub a bunch of configuration files for the tokenizer. And for example, now that we've created our tokenizer, we can access some of the attributes. So one kind of common thing that is good to check is what is the vocabulary size of the model. And so you can see here that the vocab of XLM Roberta is actually quite large. It's 250,000 unique tokens. And that's because this model was trained on 100 different languages in parallel. And so the vocabulary has to be quite large in order to kind of capture all the differences you can imagine between, say, Japanese, katakana or hiragana, and English, Latin-based scripts. The other thing that...
there's a good question, I think, right now, which is, why does every transformer come with its own tokenizer? Are there benefits in using one tokenizer over another tokenizer?
That's a really good question. Yeah, so the simple answer is that when we want to do pre-training for the model, we need to have, first of all, a data set or a corpus to pre-train on. And then the second thing we need is a way of converting the text in that corpus into these numerical representations I was mentioning. So this idea of like tokenizing and encoding text. And it turns out that every tokenizer is kind of dependent on the corpus or the data set that you're using to build your model on. And the reason for that is that there are basically kind of some statistical rules that are used based on the frequency of words in the corpus for the tokenizer to work out, should I split this word in 2, or should I split it in 3, or should I, split it in 4? And these rules are basically learned from the data. And so once you have your tokenizer on your corpus, you then use that tokenizer to train the model. And then those things together at the end is what we typically call, BERT or GPT or GPT-2. So it's really, really important that you make sure that the tokenizer you're using is the same one that is associated with the model. Because if you kind of switch them up, imagine that I use the tokenizer of BERT and I want to then combine it with the model from GPT-2, say. These are completely different tokenizers, and the inputs to the GPT-2 model will basically be very confusing. The model will just produce kind of gibberish. It won't understand exactly, how to represent this text. That's a great question. So the other thing that is kind of special about XLM-R is that it has a different tokenizer to BERT. And what Leandro showed us last session was that there are these kind of like CLS and SEP tokens that are used to sort of indicate where the start and end of a sentence is. And the same thing for XLM-R is these like kind of S or /S tokens. And you'll see these like special tokens vary between tokenizers, but they almost always have the same kind of intuition. There's something for the start of a sentence, something to indicate the end of the sentence. And you may also have something called an UNC token, which is the unknown token, which means that if something is fed to the tokenizer and it has never seen this before and it hasn't got a way to represent it, it will basically just assign it an unknown token. Okay, so we've loaded a tokenizer. Let's see what it does. So basically what I'm going to do here is I'm going to feed it some text, which is today I'm giving an NLP workshop at MLT. And the thing that's like interesting to see is, okay, what does this produce? So here we've got a dictionary, and the dictionary has 2 main fields. One is called the input IDs. And what you can see is that every kind of word in this input has been mapped now to a number or an integer. And these mappings are called like token encodings or input IDs for short. And the other thing that you can see is there's now something called an attention mask, which is, I won't go into the details of this today, but it's basically used as a way of indicating to the model which inputs should be ignored when we compute this attention mechanism that Leandro mentioned. And if you want to see kind of like this relationship I mentioned between the input IDs and the what's called the tokens, we can basically decode the tokens themselves. And indeed, you can see that, for example, the word today is a very common word in English, so it doesn't get split. And it's given a unique number of 38,396. But then there are other words which are more rare, like NLP, and this one has now been split into 2 tokens, the N and the LP. And the same is also true for MLT. So the general pattern you'll see with tokenizers is that if the word is very common, it won't get split. But if it's rare or it's kind of niche, then it will typically split it into these smaller subtokens. And the reason we do this is because if we had to keep track of every single unique word in the language, we would have an enormous input that would be very slow to train models on.
There's a related question from Aman who's asking, are these exact matches because all tokens will not be present in the initial corpus, right?
So you mean if I had something that was like unknown, for example?
Yeah, I think so. Yeah. So can it be that maybe one word is not in your vocabulary with such a tokenizer?
Yeah. So in general, there should be tokens that are unknown. I'm just trying to think what would be an obvious example. So I think more or less anything in the English language will probably get split into smaller subpieces. But what I could imagine, for example, XLM-R was trained on 100 languages. And if I picked a script that didn't belong to that set of 100 languages, then I would guess all of these inputs would just become unknown. That would be my guess. Or if not unknown, they'll be kind of scrambled somehow. That's a great question. Okay, so we've got a tokenizer.
There's another one.
Yeah.
Sorry. If our custom data has useful metadata, what are the approaches to include them in the model? Could we include our own special tokens?
Yeah, that's a great question. Yes, you can. So what you can do, I'm a bit sad that Colab is super slow for me today. I apologize. Okay, so in your tokenizer, you can actually add special tokens. And this function just requires a dictionary. So you can add like, I don't know, my special this. And then you have to provide the dictionary which relates the token to the unique number that you want to assign it. So, you know, whatever, 1, 2, 3. And then you can add these special tokens to the tokenizer. And then you just have to tweak the model a little bit so that the input size is adjusted for how to do that. But this is in the Transformers documentation if you're interested. Just look up add special tokens in the documentation and you'll see exactly how to do that. Great question. Okay, so we've got a tokenizer, and now we want to apply this to all the reviews in our corpus. So again, we're going to use our favorite function, which is map, and we just need to give the map function a function of itself or its own. And here I'm just going to apply the tokenizer to the review body. So this is where all the reviews are stored. And I'm going to do something which is very common in Transformers, which is we're going to truncate all of the text to some maximum length. So Leandro mentioned that most Transformers have a limit for how long the input can be. And for models like BERT or DistilBERT, it's typically 512 tokens. And if you don't do this, the model will basically throw an error because you've tried to give something that was too large. But in the paper on the Amazon reviews, the authors mentioned that if you truncate to 180 tokens, you actually get pretty similar results to just having the full thing. And you can train much faster. So I'm going to do the same thing here by providing these two here. Let's see if this runs. And then we just need to do again a map with our function. And I'm going to use batching because I'm running this on a GPU, and this will be much, much faster than if I was just running. I mean, you saw how fast, that's incredibly fast, right? like 1 second, and I just tokenized, you know, several thousand documents. And so if you have a GPU, you should always use batched if you have it available, and this will enable really fast parallel processing. Cool. So let's have a look at what like a tokenized review looks like. So here I'm just going to access the first element of the tokenized training set. And if Colab is going to play nice, can we run this? Great. We can see that now we've got the input IDs. So these are all the encodings that we talked about. So every token has a number associated with it, and this is what we feed to the model. We've also got the labels. So this is how we tell the model whether the review was negative or positive or good or okay, whatever. And we've also got some other columns that, you know, were from before. So now that we've tokenized the data, we have everything we need to train a model. And so you may not be surprised. Wow, Colab is so slow today. Sorry about this. This is extraordinarily slow. Okay. So once you've got everything prepared, you just need to pick, again, an auto model class for training your model. And in this case, because we're doing text classification, this belongs to a bigger category of tasks called sequence classification, because we're passing a sequence of text like a review, and we're just asking, given that sequence, what label does it have? And so the thing that you use with this auto model class is a from pre-trained function. And this from pre-trained function just expects the name of the model on the hub. And then we can provide some additional metadata, or let's say additional information about how many labels we're dealing with and what are the mappings between the label IDs and their names. And so if we run this, it's going to download Excel and Roberta from the hub. I swear to God, I must have the worst GPU in history here. Or, you know, Colab is throttling my my network. But okay, this is going to take a few seconds, but basically what's happening here is it's pulling all of the weights of the pre-trained model from the hub and some configuration files which tell the Transformers library how to take this language model, which was just pre-trained, and it's going to attach a head to this model, which is designed for text classification. And this head is all, and you know, the parameters of this head are going to be randomly initialized, and then we're going to be able to fine tune it. So this is going to give some warnings, and indeed, you'll always get this kind of warning when you're initializing a pre-trained model, and it will say something like, some of these weights were not initialized, so you should probably train the model on a downstream task, and that's what we're going to do. So now we've got a model, we've got a tokenized data set, we just need to train it. So if you've ever done some like low-level TensorFlow or PyTorch, you probably have some, you know, nightmares from trying to create your own training loop where you have to say, you know, for every batch in my data set, feed it to the model, compute the loss, do gradient descent, update the weights, all that kind of stuff, right? It's a very like low-level amount of work. But the Transformers library provides a trainer class which basically wraps all of this complexity for us. And the main thing that we need to give this are some hyperparameters. So what is the learning rate and so on. And we also need to provide a function to do the computational calculation of metrics. So if you want to find more about the trainer, you can watch this video with Sylvain. But to get started, let's just define some hyperparameters. And this is all done using the training arguments class. So what I'm going to do here, I'm going to specify how many epochs to train for. So I'm going to train the model for 2 epochs. And I'm going to pick a batch size of 16. If your GPU is like, you know, more powerful than the kind of K80 ones you typically get on Colab, you can increase this and the model will train faster. And the other thing that's important to specify is the name of your model. And I'm going to call this XLM Roberta, which is from the checkpoint name. And I'm going to say it's been fine-tuned on this MARC data set for English. And I'm just going to add here like some extra thing just so it doesn't interfere with something I did before. And then we can specify the learning rate, the weight decay, and a push to hub argument, which will automatically push all of the checkpoints to the hub for us after we're done training, so then we can interact with the model. So the first time we run this, it's going to create, did it run? Let's try again. Sorry, it's being slow.
Maybe a question in the meantime.
Mm-hmm.
Somebody was asking, can I also train TensorFlow models?
Oh, yeah, that's a really good question. So you can see here, right? We loaded a model from the hub using PyTorch. But what we can do, this is almost getting to the point where I'm going to switch machines. But if you're a TensorFlow person, you can actually import a very similar class. I'm wondering whether it's worth switching machines. What do you reckon, Leandro?
I mean, maybe you can just open the second one.
Okay, it's just, okay, I think I can only run one GPU at a time. Let's see. So I'm just gonna try to run this just because this particular Colab notebook has been extremely slow. Okay, so while that's happening, we have these auto model classes, and most of these auto model classes have a TensorFlow equivalent where you can just put a TF at the front. And so if you do that, this is extraordinarily slow. Okay. Let's see if I can use this. Sorry about this technical difficulties. Usually Colab is quite reliable, but of course, whenever you need it to really work, it's not going to work. Okay, so I'm just going to just restart. I'm starting a new notebook here, and I'm just logging in to the hub again. And here, I'm going to install this. And I just want to quickly check what kind of hardware I'm running on. Okay, so it's one of these crappy T8K80 ones. Okay, but let's see how we go. Okay, so I'm just going to run the same steps we saw before. Oh, but hang on, it's still stuck in the same thing, but let's see. Okay, that seems to be better. And we don't need that. Okay, and now I'm just going to filter the data. So one thing you can actually see, which is quite cool actually, is that many of these steps are cached by the transformers and the datasets library, so they run very fast. You only have to run them once, and then it just loads them from the cache. So let's just check this. Okay, this seems to be working a bit better. Good. So we saw here that I was talking about, okay, I loaded a model in PyTorch, but if I want to load a model in TensorFlow, I just put a TF, and then usually it's the same name that you'll see here. So auto model for sequence classification. And then I can create a TensorFlow model, which uses the TensorFlow auto model class. And it's exactly the same stuff. We just provide the from pre-trained function, we provide the checkpoint and all of the additional information. And this will now, of course, the only model that I picked today doesn't have a TensorFlow equivalent. So just to actually show what it would look like is if I didn't, I think XLMR isn't available in TensorFlow, but if I was just using like BERT, right? So BERT is from Google, so of course it's in TensorFlow. This model can be downloaded as follows.
Can't you convert the PyTorch checkpoint on the fly?
Yeah, I think so. Let's try that. That's a really good point. So if the model that you are interested in on the hub is not available in your framework, so let's have a look. If we look at XLM Roberta, you can see that it only is supported for PyTorch. If you have a model like BERT, you'll typically see that it's supported in multiple frameworks. So you can see that it's supported in TensorFlow and JAX as well. So what we could do is use Leandro's idea, which is like, okay, I'm going to take my PyTorch model and I'm going to save it to disk. So we just use the save pre-train method. And then once we save this model, we should be able to load it using the same auto class, but now instead of passing the name of a model on the hub, we're going to use the name of the folder which stores all of the PyTorch weights. And the main extra piece of magic you need is to provide a flag which indicates that this model comes from PyTorch. So I think if we do this, this should also work. Cool. So there we go. So now we have we've basically converted a PyTorch model into TensorFlow model on the fly using transformers. Great idea, Leandro.
And I think you could actually also do it from the hub.
You mean
provide a checkpoint on
trained? So here.
Yeah, and you say XLMR, and you say from PyTorch, I think.
Awesome. Yeah, so now you've seen 3 different ways to load a TensorFlow model. So yeah, it's cool.
And that actually shows a cool feature that all the models in PyTorch, TensorFlow, and checks, I think, you can convert them on the fly, which is really nice.
Exactly. Cool. Okay, so here I was creating the trainer. So we needed some hyperparameters. And once you define your hyperparameters, the last thing that we need for the model is a way to indicate how to compute metrics to an evaluation. And most of the time when you're doing like text classification, you'll use some metric like accuracy or F1 score. But in this particular data set, we're dealing with star ratings, and the star ratings are ordered, right? So a star that is 1 is worse than a star that is 5. And so we should really be if a model makes a mistake, we should basically penalize it more if the error or the distance from the true value is larger. And so what the authors of the paper suggest is that instead of using like classification metrics like accuracy, we should use the mean absolute error. And this is basically, you just take the prediction, you subtract it from the true value, you take the absolute value, and then you just take the average of all of those absolute values. And that's called the mean absolute error. So we can actually do this in scikit-learn with just this mean absolute error function. And then we just need to, first of all, get the predictions and the labels. We get the most probable prediction with the argmax. And then we return a dictionary, which has the name of the metric and the actual computation that we want to do. So once we have this compute metrics function, we have everything we need. We just need to pass the model to the trainer, the arguments, and the data sets that we want to train and evaluate on, and the compute metrics function. So if I run this, what this is actually going to do is this is going to create on the Hugging Face Hub an empty repository. Oops, this one is, I should do this differently. So what I forgot to do here, that's downloading one I was playing with earlier. So I'm going to create one here. So if the repository doesn't exist on the hub, it's actually going to create it for us and then clone it into your machine. And so if we go to the hub, you can see that we've now got this model, and inside this model, there are basically no files. It should just be completely empty. Okay, so then to train, we just do trainer.train. And this is actually quite a funny thing. So what you're seeing today is almost like what it's like to be a machine learning engineer. So things very rarely work the first time. And now you can see I'm getting this ugly CUDA error. And so if you're running on Colab, a lot of the time, the models that you would like to train on, maybe they're too large for the notebook. And so then it blows up the amount of memory. And so what I'm going to do is I'm going to restart the notebook and then not load like 3 XLMRs like we did with the TensorFlow conversion. So sorry for this live hacking, but on the other hand, I hope it shows what real life is like. So, dun, dun, dun. Okay. the other hand, it's nice that everything is cached. So for example, here, when we load the PyTorch model again, it just loads it from the cache directory instead of having to download it again, which is great. Okay, so here we go again. We define the model, the metrics, the trainer. And now, fingers crossed, this will work. Good. Okay, so what's happening here is the trainer is feeding the tokenized rows of our data set to the model. It's computing the loss of these inputs against the labels that we have. And then it's doing backpropagation and all that magic stuff that we like so much in machine learning. And this is going to take probably 10 minutes or so. But what will happen at the end of this is we'll have now a fine-tuned model, and then we can push that fine-tuned model to the hub using the push to hub function. And so while this is running, I'm going to kind of skip ahead to now looking at like what would happen if we wanted to like deploy this model. But are there any questions so far about the fine-tuning step?
I think you covered all of them so far.
Okay, cool. Okay, so I'm going to show you a model that I prepared a little earlier. So let's get this. I found out what the problem was. That map was the map of all the participants was slowing down Firefox. Okay, so what I'm going to show you now is like if you look at your models on your profile, you'll see a list here, and here's an XLMR Roberta model that I trained last night on exactly the same data set that we just looked at. And when you do the push to hub, it's going to automatically provide in the files all of the information that's needed to use this model somewhere else. And one of the cool things about the hub is that every model that has a pipeline has a widget. And so you can actually interact directly with this model, and it will give you the predictions kind of in real time. So for example, since we know the thing was trained on books, I could say something like, I loved reading the Hunger Games. And when we then do the computation, it's going to load the model in the pipeline, and then it will then generate the predictions for us so that we can interact with it. And the other thing that's like really important when you're pushing your models to the hub is the trainer will automatically give you a template of like what's called a model card. And it has some information kind of pre-filled out for you, like the hyperparameters and what the metrics were during training, and also what kind of sort of libraries were used. But the thing that's really important is to make sure that you include, for example, some description about the model, what the intended uses of the model are, and maybe some information about the training and evaluation data. Okay, so here you can see that this model was able to handle this book review about reading it. But what's cool about XLMR or XLM Roberta is I can write in other languages. So I could write something in Spanish, and it will still be able to compute what the sentiment or the star rating of that review is. And for example, if we take a Japanese example, since I don't really remember a lot of my hiragana, I could say something like, the Hunger Games was a super interesting book. So of course, assuming that I had written this myself, I can take this very different language from English, and I can then provide it to the model, and it still worked out that this has got some sort of positive association. And that's very cool. Basically, any of these 100 languages for XLMR, they will work in a relatively good way. And I think that's really cool because, in a way, language is like what kind of connects us as humans, and being able to build applications which kind of bridge the boundary between languages is really exciting. Okay, so let's assume now you've got your model that is still training, I guess, in Colab. And if we look here, during training, you're going to get some metrics about the loss. And you can see here that the mean absolute error of this model is around 50%. And, in the paper, they talk about similar numbers, like around 40% for the languages. But now you want to interact with your model somehow, because maybe you need to share it with your colleagues, or maybe you want to share it with, your boss or whatever. And so on Hugging Face, we've been working on a feature called Spaces. And Spaces is a way to share your models in a very custom and interactive way. So just to give you an example of what people have built, there's a cool example here from one of our colleagues at Hugging Face. And the idea here is I can draw a picture, and it will then take that image, it will classify the cartoon, and it will then try to work out which movie like posters are closest attached to that image. So I don't know, maybe one thing I could try to draw is like, I don't know, like maybe a cat. And indeed, it's classified my bad drawing as a cat. And it's then worked out, here are a couple of like movie posters or movie images associated with cats. And we could also, do the same for, I don't know, if we try to draw like a flower. Then still thinks they're grapes, but anyway, you get the idea. Somehow it's associating these together. So there are like many spaces that have been provided by the community. Here's a very cool one as well by Niels at Hugging Face. And the idea is that you can provide some sort of like handwritten text, and then you submit like a picture of that text. And then this model will read that text and automatically convert it into like a digital form. So this is super useful if you're dealing with lots of scanned documents and you want to somehow digitize them. Okay, so what I've shown you here, all of this is built on two main say libraries. One is called Streamlit, which you may have heard of. It's a great library for building data applications. And this particular one I'm showing you here is called Gradio. And Gradio is a very simple library for building machine learning applications with very little code. That is great if you just want to quickly demo something. So the way you build a space on Hugging Face is you go to your profile, you go new space, and then you pick a name for the space. Like, I don't know, let's call it let's call it MLT spaces demo. And then you have to pick which one of these two libraries you want to use as the backend. So I'm going to use Gradio, and you can choose whether you want to make it public or private. And then when this is created, it's just going to give you an empty repository, which has basically no files. You can clone the repository and edit it. And then you can create like a little sort of dummy file yourself. And instead of cloning this with Git, I'm just going to do this directly in the hub. So first, I'm just going to copy this bit of code. And if you go to files and versions, you'll be able to add a file. So you create new file. And here I'm going to create a file called app.py. I'm going to have Gradio like this, and then I'm going to commit this file. And then what will happen is that the application will build, and then there will be, probably some warning like we see here. And let's see what the warning is. Okay. So the warning is that I need to indicate that I want to run this in a kind of debug mode. So what I'm going to do is, this is interesting. It's pretty funny, Leandro, that like the day that you want to demo spaces, they also disable the edit button of the repository. Okay, so let me see. What should I do here? Okay, now it's working. Strange. Okay, so if I type in my name is Lewis, this is a very simple interface where if we look at the code, what it's doing is you have a function, which is just returning the name with some kind of hello. And then there's an interface in Gradio where you provide a function and you provide the inputs and outputs. And this is really well suited for machine learning, where usually you're providing like some text or you're providing an image, and then you're trying to figure out what the outputs are by some predictions. And then once you define your interface, you just have to launch the app with this .launch function. So what we want to do is we want to build something that is a little bit more exciting than just showing our name. So what we can do is if you go to the GitHub repo for this workshop, I've created a notebook for Gradio. And in this notebook, we can play around with our model using the pipeline like Leandro showed us. And then we can take that code to then build the application itself. So first, I'm just going to install a couple of things. And then what we're going to see is that we're going to use the pipeline from Transformers, and we're going to use a model that I trained yesterday, which is the same model that we're training right now. And we're going to load this model in the pipeline. Come on, Collab, you can do it. Interesting. Today is not Collab's day.
I sometimes find like the first import takes forever for some reason.
Yeah, super strange. Okay, so I'm just going to download this this model, and then we can check if it works. And so, as I was explaining in Gradio, we need to provide three things. We need to provide a function which will process the inputs. We need to provide some sort of definition of what those inputs will be, and we also need to provide the definition of what the outputs will be. So you can see here now I've got my pipeline, I've got my multilingual model. So you can see that here it was able to correctly classify this thing. And we also saw that you can write this in Japanese, in French, in German, whatever, and it will still work. So I'm going to create a little function with a twist. I'm going to basically convert all of the labels of the model into emojis because, you know, Hugging Face is an emoji company, so we should use emojis everywhere. And so if I create this predict function, it just basically reads the inputs from the pipeline and then applies this mapping. And indeed, we can see that now, if I say I love something positive, I get a positive response, which is, you know, the heart eyes cat. And then the last thing is to define this, this Gradio interface. So you provide a function which does the processing of the inputs. You provide some definition of what those inputs are. So here I'm giving a text box where we can type stuff. And then for the outputs, I'm going to look at the label and the confidence score from the model. And I'm also providing here some examples that kind of like are the defaults. So if you run this in Colab, it will automatically create the web application. And here you can see that if I put in like a review and then submit, it will then automatically compute the star rating associated with that review and give it an emoji. And we could also do the same thing in Japanese. And indeed, it's also working. So what I find really cool about Gradio is like, if you look at how much code it is, right? It's like one object called interface, and then launch. So it's kind of technically just a few lines of code. And this is kind of wrapping all of the complexity of web applications like Flask and stuff in just a simple Python library. And so, pardon me. And so then if we want to now make this application run on the hub, we do what we did before. So we go to spaces, and I'm going to create a space, MLT Tokyo 2. And we create a space like this, and we're going to just add again.
I think there's a good question from the chat.
Yep.
Do people ask, like, is spaces for free, and can you host infinite amounts of spaces?
That's a good question. So I think in the beta, it's definitely free, and I'm not sure what the future plans are regarding like pricing. As far as I know, you get by default like some kind of like limited number of CPU or definitely GPU backed spaces, but yeah, I'm not entirely sure how far you can go. I mean, you can try, right? I mean, if you want to launch 1,000 spaces, maybe at some point you'll reach the limits. And in fact, if you make 1,000 spaces, that would actually be pretty cool. So I do encourage everyone to just create as many spaces as
long
possible.
as it's very unique and interesting.
Yeah, definitely. Great question. Okay, so I've got this space, which is basically empty at the moment, and I'm going to add the app.py file. So here I just basically need to copy paste the code I have here. So I'm going to first just copy paste the imports. So we put that in the file, and then I'm going to copy the pipeline. And then we also want this function that does the processing of the inputs. And then the last thing we need is just the Gradio application itself. And then if we commit this file, it should start building the application. And most of the time, there are like some base requirements that will be provided in the space. But if you don't have everything that you need, for example, we don't have transformers, you can add a requirements.txt file. And here we can provide all of the requirements that we need. So I think we might need torch transformers, and let's just put Gradio for good luck. Okay, and so then this is now going to automatically install the requirements that we need. It's then going to build the application, and fingers crossed, if I didn't make any mistakes, we'll have a very own interface and model running on the hub. So while that's building, are there any questions?
Somebody asked whether like the UI is customizable.
Good. Yeah, that's a great question. Okay, so Gradio, if you go to Gradio app, they provide in their particular documentation like sort of what is and not customizable. So if you go to the docs, you'll see some of the things you can change in the interface. But if you want to be really custom, you can check out Streamlit, which is much more flexible in that sense. And there's a really nice example here of like, I don't know, maybe it's, do we still have DALI on the hub or not?
Not sure.
DALI Mini. So here's an example that's been built with Streamlit. So it's got a different interface. And, I can say here, give me images of, I don't know, a dog walking on a beach or something. And this is much more customizable, and you can provide some messaging and stuff like this. And, I would suggest using that. I don't know how long DALI takes to run, but let's give it a sec, because this is actually quite a cool. So yeah, For those that don't know, DALL-E is this very cool model from OpenAI where they basically trained a kind of text to image transformer. So you can type text and it will then try to represent that text as a picture. And this model is like a small version of it that was trained by some community members. And so, yeah, now you can see that, it's kind of getting dogs, but it needs a bit more training to do better. So let's see if our model or application has built yet. Not yet. So usually it takes a while to start because it has to install everything, like especially Torch, which is always a pain, but this is now running. And why is today is not my day? Okay, it's still downloading the model. Okay, so this is just waiting at the moment to download XLMR, Roberta, which takes a couple of seconds, I think. But anyway, you get the general gist of what's going on. Yeah, so that's kind of in a nutshell how to go from like a raw data set all the way through to training a model, to pushing it to the hub, and then using that model that's on the hub to build an application.